So in this video, we talk about virtual memory. So we know that cache memory enhances the performance by providing faster memory access speed. On the other hand, virtual memory enhances the performance by providing greater memory capacity. So without the expand of the adding main memory, um, instead of a portion of the disk drive serve as the extension of the memory, and if a system using a paging of a virtual memory partition main memory into individually managed page frame and that are written or paged to disk when they are not immediately needed. Okay. Um, the concept of the physical address in virtual memory that the actual memory address of the physical memory. Um, the program creates virtual addresses that are mapped to physical addresses by the memory manager. And also we have another concept we call a page fault. This occurs when a logical address requires that a page be brought in from the disk. Another concept in the virtual memory is that the memory fragmentation occurs when the paging process results in the creation of small unusable cluster of the memory addresses. So in this case, if we without a careful management of the memory, we can maybe divide the memory into a different cluster where they have the very small size we cannot use to drive some specific data. Um, the main memory and virtual memory are divided into equal size pages. The entire address space required by a process need not in a memory at once. Actually, some part can be on this, and while the other part can be in the main memory. Further, the pages allocated to a process do not need to be stored contiguously, either on the disk or in the memory. So by doing it this way, we can see that only the needed pages are in the main memory at any time, and the unnecessary pages are in a slower disk storage. Okay, so by doing this, we don't need to have a large of the memory, but we still can improve the performance by reduce the accessing time to the data. So here's the graphical representation of an example. So in this way, you can see that basically we have the information concerning the location of each page and whether on this or the memory. So this information is maintained by a data structure we call a page table. So here's the page table here example. Um, uh, uh, the graphical representation here is represent one page table for each of the active process. We have the virtual memory that have the size of 8 from 0 to 7, and the physical main memory have the size of 4. So we have from 0 to 3, and also we have some kind of pitching between the virtual memory and physical memory. So the based on here, you can see that the page number right here from 0 to 7, and the page table here gonna represent the frame number and also the valid bit as well. So we can see that the page 0 in the physical memory gonna be a have the frame number. This is frame number 2 that's corresponding to the virtual that's corresponding to the frame in the physical memory. And when that's the case, we have the valid bit equal to 1. On the other hand, the page number 1 right here doesn't have map to any of the physical memory. That's gonna be empty, and the valid bit equals 0. The same for page number 2. That's have no information corresponding to the main memory, so we have the valid bit equals 0. On the other hand, page number 3 right here gonna be um, corresponding to the physical memory of the frame 0. So we can have the frame number 0 here, and the valid bit is set by equal to 1. and so on. Okay, so basically we have the frame number that represent the location in the physical memory, and also if that's okay and the information from the virtual memory have been marked to the frame number, the physical memory, we're gonna set the valid bit equal to 1. Okay. So when a process generates a virtual address, the operating system gonna translate it into a physical memory address actually. So to accomplish this, the virtual address is divided in two fields. One the page field and another one we call offset field. So basically the page field determine the page location of the address, and the offset field you to indicate the location of the address within the page, and the logical page number is translated into the physical page frame through a lookup page table, as we discussed before. We also can see that the valid when the valid bit equal to 0, the page table entry for that logical address is just mean that the page is not in the memory and must be fetched from the disk, and that's gonna occur a page fault, and if necessary a page is evicted from the memory and is replaced by the page retrieved from the disk, and the valid bit is set to equal to 1 when we retrieve from the disk and put into the memory. On the other hand, if the valid bit equal to 1, this means the virtual page number is replaced by the physical frame number, and the data is then can be accessed by adding the offset to the physical frame number. Okay, so that's basically some concept of the virtual memory. We're gonna show some example related to virtual memory later on.